Day 100, honors, refraction, problem number 28. All right, you're going to need to locate your geometry belt here and your physics helmet, because this is going to be some warfare. This problem is a little detailed, so watch out and pay attention. So I've taken this diagram, as you can see, and I've blown up the middle part of it, and I've calculated the first angle of refraction. There's going to be a lot of angles here, and I'm not going to repeat subscripts. So I'm going to go from theta 1 to theta 2 to theta 3 to theta 4 and so on and so forth. Each time I might be applying Snell's law to two more new angles, but in that case I won't call them theta sub 1 and theta sub 2, but it might be theta sub 5 and theta sub 6. All right, so bottom line, though, first case here, theta sub 2 as illustrated with Snell's law is 13 degrees. That's the first angle of refraction for the entering ray over here on the left. Our ultimate goal is to find this D down here, but we're going to get to that in about 5 minutes. All right, let me pause and go to the next slide. Well, actually, before I do that, one thing to notice, here's what I mean by putting on your geometry belt. Hopefully you remember that this angle right here, which is alternate interior with theta 2, I'm going to call this theta 3, however, theta sub 3. Theta sub 3 is alternate interior with theta sub 2, so therefore theta sub 3 equals 13 degrees. I'm going to use that in the next diagram, and then I'm going to, well, we'll see. All right, what I've done is I've highlighted this red triangle, and this is what I mean by putting on your geometry belt. Just pay attention here. There's a lot of things going on. There's more than one way to solve this problem, but I've done this problem before, and this is one of the more efficient ways of solving it. This red triangle here that I've highlighted has that thin angle 13 theta sub 3, which was the alternate interior angle to our first refracted angle. And this length here on this leg is 2 centimeters. I didn't pull that out of just nowhere. It's the 2 centimeters thickness of this crown glass. And if I go straight across, perpendicular down the short leg here, this is the hypotenuse. I'm calculating the length of that hypotenuse for reasons you'll see here in a few minutes. So I did that down here on the bottom left. H is 2.05. Now, the main thing we're after here in this problem is down here on the lower left is this D, which is how far apart these two lines are. I'm going to use blue. That segment right there is perpendicular to these two rays, the actual ray, and then this dashed line, which I'll just kind of highlight a little bit of, lines up with the exiting ray way over here on the right. I'll do it in this small diagram at the very top. So this right over here all lines up. That's one extension. So we're trying to find the distance between that final exiting ray way up here on the right. We're trying to find the distance between that piece and the original piece down here on the left, D. All right, so what I'm going to do is I'm going to draw that same blue segment right here. That segment I'm drawing is perpendicular to this dash line. That's the main thing. So I'm going to draw that leg and draw this thin blue triangle. It's a right triangle. I'll go over it a couple times so you can see it, which shares a hypotenuse with that red triangle, but it's not the same size triangle. It has the same hypotenuse, but it does not have the same other two complementary angles. For example, this angle right here, let me use my, well, between the two thin angles of the two triangles, the red triangle has this 13-degree angle right here. But what is this little thin angle of the blue triangle? It's not 13. But what I can show pretty easily is that this whole angle here together, the 13 plus that little blue angle, has to be 20, because it has to be, well, it is what's called a vertical angle with a 20. Once again, I'm pulling some geometry out of your knowledge bank from a few years ago. Vertical angles are equal. So if I have 20 degrees over here, then I must have 20 degrees over here, because they are just extensions of two lines. They're called vertical angles. What that means is, pretty easily done right now, is that angle right there is 7 degrees, because 13 plus 7 is 20. So on the blue triangle, the thin angle is 7 degrees. And now you might see how this is coming together, because I know what H is. And since I know what H is, if I'm looking at that blue triangle, because that's the same for both, I can use, because what I'm after is D. And this segment right here, this short leg of that blue triangle, is distance D. That's what I'm looking for. So I think if I just use sine of 7 degrees, sine is the opposite leg, the length of the opposite leg, which in this case is capital D, divided by the hypotenuse H, in this case, which is 2.05. So I plug that into my calculator, and I get D equals 0.25 centimeters, which is 2.5 millimeters. Now, I don't know if I made that look easy or not, but believe me, that's not so easy when you're put on the spot and have to do it on a test. But that's what we're looking for. The distance of separation between these two beams, the deviated beam from the original beam, a distance of 0.25 centimeters.